So the limit comparison test, comparing two series without indirectly through the limit of their ratio. The limit of their ratio is what we have to consider, and depending on what that limit is, we have three possible answers. The fourth case is what's the fourth case here? These are the three cases. Is there other cases?
It just doesn't exist.
Well, right. So it is something to worry about. It is possible that the limit doesn't exist, and so in that case you have to what's the answer? The theorem doesn't apply. So careful about that. So such a sequence could an over bn conceivably could go up and down and not converge to anything, whether either a number or infinity. So that's the fourth possibility. I will add it in a kind of informal way here. So does not exist. Test fails. You may have seen this before. Such an option, which is not really technically an option. It brings you outside of the theorem, so it's not a part of a theorem technically. So anyway, this is how you compare. So you take the limit. If the limit is a number other than 0, then the two series are comparable in the sense they either both converge or both diverge. And then there are certainly these kind of not entirely in the right order. The right order would be what L is equal to infinity, L is less than infinity, larger than 0, and L is 0. Okay, so then these are the two extremes. The two extremes are when one of the two series dominates. Okay, so either AN dominates or BN dominates, but not, once again, not directly as in the form of an inequality, but just long-term behavior is one series is stronger. So in the top case is what is it? The numerator AN dominates BN. Here, conversely, it is being dominated by BN, and here they are similar, like this. And so once again, the way we express that, the middle case, the middle case is here either both diverge or both converge. So these are the three main cases. Okay, so the point of this is discover more convergent series or divergent series, not like that example that we see here, which is you are given two series and then you demonstrate, then you know what the comparison is automatic. It is more typical to receive the problem in the form of with only one series, such as say 1 over square root of n squared plus n plus 1. Okay, so does the series sum an converge or diverge? Okay, so that's a more typical situation. Then you have to figure out what to compare it with. Okay, so that is something that is there is no straightforward algorithm for finding such a series. So you have to look at and anticipate what's going to happen under the limit, and then you pick. It is the ideal situation is in the middle. Okay, not one or the other. Ideally, when you don't know what the answer is, you compare the series to a series that is comparable. So this is comparable or similar, and but familiar. How do you beforehand know that is comparable? Look at the powers. So if there are powers involved, then the power of n is what determines the long-term behavior of the function, whether it is the denominator or the whole fraction. So so you look at the denominator and ask yourself, what is the power of n altogether? What is the power of n? The highest power of n. You remember, once again, the powers don't matter other than the highest one. So what's the highest power? No. What about the square root? Yeah. So it is a fair way to say that n is in fact, it's the highest power of n is 2, and then it's a quadratic polynomial, so it is the power of n is 2, but then it's inside of the square root, which makes it the answer becomes 1. Okay, so it's like you start with the square root of n squared plus n plus 1, then you replace it with, you get rid of the lower degree terms. So these terms are not important. So you're left with a square root of n squared, and which gives me n. And so the power is 1. So the answer is 1. And then you compare it then with your series with bn equal to 1 over n. Okay, so it is a much simpler series. It is also a series is known to be divergent. So the sum 1 over n is divergent, so that's good. So that comparison, if we can pull it off, will give us the answer. So what do? We just take the limit. So we take a n over bn. So 1 over square root of n squared plus n plus 1 divided by 1 over n, which gives me, what is it, n divided by the square root of n squared plus n plus 1. And you need to find the limit. You find the limits, and in that point there are several ways to do it. So even though we are still talking about sequences, keep in mind that when you talk about limits at infinity, the techniques that you applied or methods that you learn in Calculus 1 about limits at infinity of functions, which give you possibly horizontal asymptotes, it's all still applicable. So just replace n with x and you're fine. Okay, so if that's what you choose, it's certainly up to you. So I'm hinting at L'Hopital's rule as always. A good idea. Or you can just to do some algebra and simplify things. And I would say factor, put everything. What should I do? I think I will. I would put the square root inside, outside, and I have n divided by n squared divided by n squared plus n plus 1. Okay, and so what's the limit? So look at the fraction. It is simpler probably to start with the fraction itself and ask yourself what the limit is of that thing. The limit is 1, and how do you know? Yeah. Either one of them works, and so just 2 words would explain the whole thing. So you can say L'Hopital's rule or powers. There was a theorem in Calculus 1. You compare powers, so if they match, then all you have to look at the fractions. So either way, it's the limit is 1. Then what's the answer for the whole thing then? Square root of 1, which is 1. Okay, that's fine. It does require a little bit of an explanation why you were able to handle the root, the square root in this manner. Remember what the explanation is? You're dealing with a limit, and there is a function inside the limit, and you want to pull that function outside of the limit, which is what we did. We took this 1 and put it here, okay, like this. So like this. 1. It's the same 1. Okay, so what is the justification for such a step, if you remember? Because the square root is continuous, right? Technically, it's continuous at continuous at 1 works out perfectly well. If it was at 0, then it would be one-sided continuity. Okay, so the limit is 1. 1 is that is my L. So L is equal to 1. Then by the limit comparison test. What do we have? Then we conclude that both converge or both diverge. So the series AN diverges. Okay, so it goes without saying that you have to make sure that the series you're looking at it has positive terms. So this one is, and that's why it works out. Okay, so that's pretty much how it works out every time. You can think of more complicated examples, but it doesn't really matter. It doesn't have to be more complex than that. You just that's the technique. That's the technique. Strip off all irrelevant pieces of the. That's the step number one of your sequence. So to simplify it as much as possible, if it works out right, you have a series that is familiar, and then to make sure that it works out, you still have to carry out that computation of the limit. If the limit is the right one, such as a number, then you have your decision. So you know what the new series is like. So in this particular case, we discovered that BN diverges, then so does the AN, the other one. Okay. So I did not specifically state it here, but certainly that becomes the next is to we will have to face that what to do with a series that have no not necessarily all positive terms, and that is very, very crucial. In fact, just take an example of what the whole motivation for studying series has been. Power series like this. So in other words, this is AN. So power series is x-dependent series, and so every term is that part is still the same. So it is a bunch of terms being added together, and but then we ask ourselves, does this under what circumstances this thing, this AN that we're looking at is positive all the time? And the answer is pretty much never, because as x varies, you will every time you might be positive or might be negative. When it is odd, it will definitely change the sign at A. So x hits A and it changes its sign. That expression will change its sign from positive to negative. So then it will be impossible to study the series as a whole, rather than checking out every value of x at a time. So that simply is not going to work. So not necessarily all positive. So that's a problem, and so then we have to find a way to find better ways to study series that are with any kind of terms. Okay, so it is not, turns out to be quite manageable, but the idea is, well, let's start with a few examples to see the difference. To begin with, that's one example when you see a series that has various terms. So various terms, not necessarily positive. The typical example of that is alternating series. So that's an example. Not necessarily not all series are either all positive or alternating, but this is a good example. So one is this, -1 to the n. By the way, you may have noticed that I started to omit more and more often. I started to omit the indices, the summation bounds. So as you can see, originally I put, where is it? Well, this is these are important, but not that important as it turns out, because so as you can see once again over here, look at these. I omit the bounds. Why doesn't matter. So I still have bounds here, but in general it doesn't matter that much, because why not? Because we adding or removing several terms from a series or sequence or series does not change its limit. It does not change its sum. So since we're not really right now in business of trying to find what the sum is, then it doesn't really matter. We only care about whether it is a number or it is not a number. So then convergence and divergence is independent of that fact, whether or not you have a few extra terms. So you can start at 1, you can start at 0, or at any number larger than 0, less than 0. It won't make any difference as far as convergence is concerned. So then it is slightly informal attitude, but it is nonetheless totally safe in this environment to ignore the limits. Okay, so and that's so I continue doing this. So -1 to the n, alternation between -1 and 1. So this one diverges. Okay, alternating. Well, what does it mean? Alternating. It means that the terms of the sequence alternate between positive and negative. So that's the simplest example of an alternating series. It diverges. But there is another one, and that is -1 to the n over 2 to the n. So as you can see, that's what -1 to the n does. It alternates the sign. So n goes odd, even, odd, even, odd, even. Therefore, -1 will be respectively 1, -1, 1, -1. Okay, so whatever follows that -1 to the n term will, if it is all positive, then that exactly what's going to happen. The sign will still alternate. So this particular series is in fact, so if depending on where you're starting, let's say we're starting with 0, okay, so then we have 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16. So as you can see, as you can see, the terms are the same as in the geometric series that we started our studies with, 1/2 plus 1/4 and so on. But the signs alternate. So so the question becomes, does it converge or diverge? And does it converge or diverge? Can you tell? Well, there's a trick. There's a trick here. I can simplify the series itself. Can I simplify it? Well, what can you do with that expression? Well, there's not a lot of things you can do with it. You can merge them. You can merge them together. It's the same power of n can be distributed over the two terms, so it will be simply -1/2 nth power. Okay, so what kind of series is this? -1 taken to the nth power. So to progress on and on, you multiply by -1 at every time. What do we call a series like that? Multiply by the same number all the time.
That would be a constant.
No, not a constant. A constant would be sum of ones, or ones. Sum of ones, that's a constant series. So it's 1 plus 1 plus 1. So the terms don't change. Okay? So then you go to infinity, positive infinity, or one or the other, unless it's all zeros. But here I multiply by the same number all the time. This is geometric series. All the examples that we have seen were about multiplying by the same number, well, actually, if you might, this is also a geometric series. This is a geometric series, but so is this. Okay, the difference is the ratio. And the ratio, what is the ratio? The ratio is that number is that you keep multiplying by your terms. So to figure out what the ratio is, you just either look at the formula or just write it in a recursive manner. So you multiply in the latter case, you multiply by -1. Sorry, -1/2 every time. -1/2. -1/2, and that's how powers start to accumulate. So the example that we saw before, it was 1/2 was the ratio, so you multiply by 1/2 every time. But you can multiply by -1/2, and that way you simultaneously getting smaller and smaller terms. At the same time, they also alternate in sign. That's what -1 does. And in the latter case, the ratio is 1. I'm sorry. The ratio is -1. So there is nothing but alternation. And then to find something out about these two series, all you need is the geometric series theorem. And what it says is that depending on this, the absolute value of R is what determines whether a series converges or diverges. So this one, R is equal to 1, that is why it diverges. And here the absolute value of R, which is 1/2, is 1/2, and it is less than 1. Remember that theorem? So the ratio, absolute value of the ratio is less than 1, we have convergence. So this one converges by the geometric series test, or just theorem about geometric series. Okay, so we have two convergent series. So just to confirm that we can converge even though the terms are not positive. So that previous analysis of positive term series, it is limiting us significantly. We cannot prove things about series that are with those tools. So as an example, once again, a better example, I suppose, in other alternating series is some -1 to the n divided by n squared. Okay, this is not a geometric series. So you cannot express it in terms of multiplication by term. It is in fact, if you ignore -1, if you ignore the numerator, it is a p series. It is a p series. So if you want to compare to something familiar, then you take the p series with p equal to 2, and that one is convergent. Okay. However, how does that help? Okay, so we're looking at two series. We're looking at these two series, and then we might want to compare them. So let's say this is AN and this is BN. None of the theorems that we have seen so far are helpful because one of the series does not fall into this category. So this one is larger than or equal to 0, but this one positive and negative. So the comparison test, or let's say limit comparison test, does not apply, unfortunately. Okay, so then it is all our guess of what the convergence is, whether this new series converges. We could try it, and that certainly is a step in the right direction, is to try to put it between, try to squeeze it. So I have a -1 to the n over n squared. It will be less than or equal to 1 over n squared. Okay, so if you try to, I mean, we know that this cannot possibly work. We cannot possibly expect the theorem to apply. Once again, same reason. So limit comparison test does not apply, and the direct comparison test does not apply either. Because of that, direct comparison test does not apply. So that inequality is really might be nothing. But let's examine it anyway. So because we know that this series of 1 over n squared is convergent. Okay, so does it help at all? And on the surface it does not, or it should not. You should see that it does not converge. That's the question that came up at the very beginning of the class. it is possible that the limit of the partial sums of the second sequence, the first sequence, would alternate and diverge, because remember why we started positive series, because the partial sums become monotone and they either go to infinity or they do not. When they do not, we have a limit. We have a convergence. When we have alternating or series such as this, these partial sums will go up and down. Okay, so they might start oscillating. So let me show you a picture of here it is, of that, exactly that. So as you can see, we have two series are visible here. The dark one, so look at the first picture. I have those two series right there side by side. So the dark brown is, light brown is 1n. I cannot write this. The light brown is 1n squared. Okay, so light brown is 1n squared. Okay, so as you can see, the light brown bars all stick up above the x-axis. So that's a positive term. Now, how do we create the other one? One at a time, or rather skipping one, we turn it upside down. So that's what happens. So if now we're looking at the dark one, this one. As you can see, it's exactly the same, and this is exactly the same as well. And over here, they're also exactly the same. However, once in a while, we turn it upside down, because we make it negative, because negative sign alternates between 1 and -1. So one at a time will be same, negative, same, negative, same, negative. So as you can see, then that these are the two sequences, AN and BN. So AN is the dark brown, and the light brown is BN. We know that one. Okay, so once we see the relation between the two, that inequality you can see it here. It is in fact, so you can see it right here. Why that this inequality? Because either these two things are equal, or when n is odd, equal when n is even, and the opposite sign when n is odd. Okay, so that's what we're seeing here in the first picture. Okay, now what if we start adding them up? You can see what's happening. So the light brown will produce. So these are partial sums that I'm plotting here. Partial sums. Okay, so the original sequences are in the first picture, the partial sums in the second picture. And the partial sums of the original P series are in light brown, and we know that they converge. They converge to the sum, and we even have roughly what that idea what that number is. And then you can see what's happening to the second picture, the second row of all those dots. So once again, partial sums. Well, first of all, but where do they come from? I take those bars and add them up, so stack them up. So I take one light bar, and then the next light bar put on top of it, and then I end up with these dots in the second picture. Okay, and then I do the same with the second series. Okay, so as you can see, the relation is kind of clear when you add the original, but rather the second sequence, the P series. If you start adding this up, then it will be growing little by little, slow, but it will be growing. In the meantime, if you deal with the second, you can see what's happening. It goes up and down, just as promised. Why? Because we alternate. We add a positive number, then we add a negative number. Positive, negative, positive, negative, and that's why it goes up and down. That's alternation. Alternation between the sign of the original series becomes alternation of the direction in the series, in the partial sums. So it goes up and down. That is quite clear, and it is getting that swing gets smaller and smaller. Okay, so from this you can guess already what is the you can guess that the second series is also convergent. So even though it is not really held down by the top curve, but it is in fact, but it does seem to be convergent. So that seems to be there seems to be here some kind of pattern here. So convergent to whatever that number is, I don't know, 0.9 or something like that. That's what appears to be. This seems to be convergent to I don't know, 1/6 or something like that. But this one is convergent to a number that is smaller. So if it is convergent, certainly convergent to a smaller number. But this is just a picture that is suggestive, and but the picture is quite I think very suggestive in the sense of how it starts to accumulate, and that swing is what holds it down. So so the only question is, how do we really prove? How do we make that assessment? How do we conclude that convergence on the right produces convergence on the left? Okay. And one way is to do it this like this, -1 squared. Okay, so that is, even though step in the right direction does not really tell us anything, because we're only comparing the two sequences, three sequences, and the best we can say by the squeeze theorem that they will be convergent to the same number. And what is that? What is that number? What is that number? (1n squared) converges to what? 0. Okay, negative of the same thing also converges to 0, which means that by the squeeze theorem, what's in between will also converge to 0, like this. Okay, because so left and right go to the same place, which means that whatever in the middle also goes to that place. Okay, that's all fine, which only means that that new series passes the divergence test. Okay, so but that's necessary. That is not sufficient to conclude that it is necessary to conclude that it is convergent, but not sufficient. So this is not enough, and some kind of comparison test is necessary. And in fact, there is a hidden direct comparison test here within this algebra. So this is the idea. We subtract. What do we subtract here? Okay, we add 1n squared. So add 1n squared to all three parts, which means that the inequality will still be the same. So -1n squared plus 1n squared less than or equal to -1 to the n on squared plus 1n squared less than or equal to 1n squared plus 1n squared. Okay, so I added one term to all three parts. Things simplify significantly on the left. It is definitely simply 0. And on the right, it is the same thing repeated twice, so it's twice 1n squared. Okay, so then the series in the middle, it cannot be simplified, but that's okay because well, we'll see why it is okay, but the accomplishment is to be appreciated now, what we have accomplished with this little trick, and that we have a new series. Well, let's recognize what these three parts. This is still unknown, so this is but it is familiar in a certain sense. This one is convergent series. Okay, and this is simply 0. The point being that the inequality gives us a series, new series. This is the new series. It is in fact a positive term series. So that's why we did the trick, is to convert this kind of oscillating thing with neither of the comparison tests applicable. To convert the situation to the state when it is applicable, and it is. As you can see, we have 0 on the left, and indeed that series, even though it looks complicated, but really it is now, we are in the position to apply the direct comparison test. Why? Look at it. This new series that is unknown, however, it is smaller than a convergent series. So once again, that 1n squared multiplied by 2 by the constant multiple rule, the series is still convergent. So it was 1n squared convergent, still convergent, and so we have now a series, now a sequence of our series, is squeezed between 0 and a convergent series. So, which means that by the direct comparison test, this in fact is convergent. So -1 to the n over n squared, that is a series, let's call it Cn, is plus 1 over n squared, converges by the direct comparison test. Okay? So positive term series less than a convergent series, it also converges. Okay, so how does that help? While our interest is not this series, but rather this one. This is our interest. Well, fortunately, I mean, this simple algebra will give us the answer, because our series, which is an equal to -1 n over n squared, is in fact equal to Cn minus 1 over n squared. Okay, and then what? And then both of these series are also convergent. Convergent, and Cn, well, wrong arrow. Convergent. Cn is convergent, and 1 over n squared is also convergent. So, by the so sum an is convergent. By what? By the sum rule. The difference of two convergent series will give me a convergent series. So, okay, so we have proven that that alternating series in the box is in fact convergent. Okay, and that is the technique for studying series that are not necessarily positive terms. Is a subtle step that we made. I'm not gonna. This was a clever trick over here, but over here. But we're gonna use it. We're gonna implicitly use it. But really, the subtle trick is that we're gonna be using explicitly is this. What is the relation between these two series? And the answer is it is the absolute value. One is the absolute value of the other. Okay, one is the absolute value of the other. So if we take a series and take the absolute value of its terms, you get a new series, and that new series will have only non-negative terms. And then all the techniques that we have learned in the recently apply, and those are the direct comparison test, the limit comparison test, and even the integral comparison test. All of those require positive terms, and that will be totally applicable. Okay, so that's as you can see what we have. Let me state the theorem first, which I implicitly proven here. So this is the first theorem. So we have this inequality. Two series, an squeeze between negative bn and bn. Okay, bn is larger than or equal to 0. Okay, and then as what we just demonstrated, that if the bn converges, if some bn converges, then so does some an. It is a kind of a version of the squeeze theorem for series, I suppose is a fair way to call it, but it's more subtle. And as you can see, that we just would prove that we looked at actually it actually does not use the squeeze theorem at all. It actually uses something entirely different. So that the theorem is a stepping stone to the theorem that we really want to rely on, and that is about convergence of absolute values. Okay, and the convergence of absolute values of a series is called the absolute convergence. So definition, sum an, well, let's just use words here more. a series series AN converges absolutely if its series of absolute values, if the series of absolute values some absolute value AN converges. Okay, so as you can see, that's the explanation of the word absolute. It refers to the absolute value. Okay, so from an old series, which might be alternating, we produce a new one that is have positive terms, and then if one converges, then we call converges absolutely. It sounds like sounds very absolute. It sounds stronger. Absolute converges sounds stronger than convergence, right? It is, which is nothing in the suggests here that is the case, but actually it is. It turns out to be true, and so we'll get to that later. But let's first restate this theorem that we have stated at the top. So because note this, how does it apply? This is how. So whatever AN is, we have AN lies between negative absolute value AN and the positive value, positive of the absolute value AN. So that's what my BN is. It is the absolute value of AN. That's the most interesting application of this theorem, is to choose BN in a specific manner from AN by taking the absolute value of these terms, and then that's how you have to create the squeeze of that sequence, and then that proves indeed. Let me. So once we realize that, so always this true. This is always true. AN is squeezed between the two sequences. I probably could see it here in the first picture, but I probably just make a picture to illustrate this idea. So I have my AN, hypothetically, suppose it alternates. Suppose it, so AN is, say, green, so AN, and it alternates like this. Maybe like this. So this is my AN. Okay, then how do I plot? Let me plot the absolute value. Well, actually, two sequences, as you can see, two sequences, AN and BN. Stop it. What are you doing? Okay, let me start over. Close it. It crashed, I'm afraid. Okay, starting over. Okay, so let me try again. Okay, so okay, so it's not doing well. Not doing well. Okay, so let me just try to plot so this is AN. Let's plot the other two sequences. So one will be positive terms. That's what's on the right. So every green bar that is below the x-axis, I pull it up like this. Okay, so like this. I turn it upside down like this. So then this becomes absolute value AN. On the other hand, I can turn positive ones down like this. Okay, and then this is the negative absolute value AN. So my AN, as you can see, the green ones are squeezed between the two. Okay, So, and then the idea is that well, we have that squeeze, and the theorem at the top gives me my conclusion, which is what I wanted to say anyway. So the theorem, if some an converges absolutely, then it converges. Just to explain the language. So indeed, it sounds strong, converges absolutely. So then, as you can see, it definitely converges. So yeah, so the language, even though absolute comes from, the word absolute comes from the absolute value, nonetheless, it is applicable. It contains more information than it seems. So because absolute convergence includes convergence. Okay, so so based on this theorem, for example, that sequence we started with, let's redo it. Sum 1 over n, negative 1n over n squared. Okay, so that an is equal to negative 1n over n squared. Okay, the absolute value is what happens? Nothing. You just remove the negative sign, so you have 1 over n squared. You know that sum an 1 over n squared rather is convergent. Okay, so well, so it means that sum negative 1n over n squared converges. Converges absolutely. So it converges. The term converges absolutely is so important that we, in fact, I put the last conclusion in parentheses because we rather, if we know that it converges absolutely, we'd rather state that and do not proceed and to, kind of proceed to a conclusion that is obvious and doesn't contribute anything more. So most of the time we'll be speaking of absolutely convergent series. Okay, so see you tomorrow.